today I'm going to talk about DC-DC converter control loops, what they do, what they are, and what are the stability margins. What's the idea behind the stability margins? Then how is the loop gain measurement technique working in itself? What's the idea behind that and how does it work? Some hints for successful measurements and some words on safety, and then talking about the PFC loop measurement, the voltage loop measurement, and then switch to a live example here in our symposium. Yeah, the DC-DC converter on itself is basically, we have a dynamic system. That means we have a closed loop system with negative feedback, and I would like to use a laser pointer. Good, so here we are. So we have our power stage. In that case, that would be a boost stage, and then we have the output voltage, and in simplest case we have only a voltage feedback, and with my slides I will only talk about the voltage feedback only. If you have a current mode controlled converter, you always have an inner current loop and an outer voltage loop. But in current mode, like peak current mode for example, then usually it's considered that the current loop is changing the transfer function of the power stage, and then actually also only the voltage loop is compensated using a traditional compensation method. So also that is the only one that needs to be analyzed. If you're talking about average current control then, or digital systems with digital current control, then you might be interested in measuring both loops separately. But the idea is that we have a dynamic system that can react to sudden line voltage changes or to changes in the reference voltage or in the set point. If you think of an inverter, then it's basically a switching converter that follows a sine wave, or also the PFC, the inner loop is actually following the sine wave so that the current matches a sine wave input current. And the question often arises, how can we optimize a compensator? So how can we place the poles and zeros of the transfer function of the compensator to achieve a stable system? Or how can I verify control loop stability in such a system? There are different ways. One idea is to use an analytical analysis, and that can be quite challenging. Another idea is to use a working presenter stick. So here we are. Another idea is to use simulation. We have seen that in our first presentation from Christopher Basso on simulation. And you can do time domain analysis, you can do frequency domain analysis. There are different possibilities what can be analyzed. Then we have time domain experiments that would be using an oscilloscope, and we will also show a step load response in this session afterwards. And then the main topic of today is frequency domain experiments, so using a VNA or an FRA, vector network analyzer, or a frequency response analyzer to measure the transfer functions directly in frequency domain. Yeah, looking a little bit more closely into our voltage loop of such a converter, we see the switching converter here. That's the power stage. We have the feedback. We compare the feedback with a reference. We compensate the error, and we create a new duty cycle for the PWM that switches our power switch. And if we follow that loop, then we can say the output voltage is composed of the difference between the reference and the output, that would be the error voltage, and then multiplied by the transfer function of the compensator and multiplied by the transfer function of the PWM module and multiplied by the transfer function, the duty cycle, to output transfer function of the power stage. That's the complete system that we have here, and multiplying all these transfer functions together, that gives us the loop gain that I denote with T of S here. So that's the product of all the transfer functions in the loop. When we talk about closed loop transfer functions, an important transfer function is the reference to output transfer function. So for the PFC, that would be how well does the current track the set point. So how well does it track the sine wave? So reference to output in closed loop. We can do the math, we can restructure the equation that we had before, and then we will arrive at an equation that is very well known and popular. If we replace the loop gain by T, then we have that well-known equation that is T over 1 plus T. That this is this over 1 plus T, that comes from the negative feedback. And what does it mean if we have a large number for t? So if it's a large number, we have the equation, the result will be a large number divided by a large number plus 1, which is basically 1 in the end. And that means that the output tracks the reference, and that's exactly what we want to achieve. When we look at the line to output, so input voltage changes and how does the output voltage change, that would be the PSRR. So if we have transients on the input, we don't want them to show at the output. And if we know the open loop transfer function of our power stage, so from the power electronics components and the duty cycle, then the equation changes that open loop transfer function to a closed loop transfer function when we employ the negative feedback. That is the open loop value divided by 1 plus t. And again, if the t is a large number, then the result will be, in this case, a small number, because something divided by a large number usually gives a small number. And small number means nothing goes through, so we have good ripple rejection from the line to the output, at least up to the loop bandwidth. That also means we have high PSRR, or out of expectability, up to the loop bandwidth, and that's usually what we want. Now let's talk about the loop gain itself, the open loop gain. So from what we heard before, we learned we need high loop gain to have good output regulation and good ripple rejection. If the loop gain is not a large number anymore, then basically it doesn't change the transfer functions that much anymore, so the feedback loses its effect. But high loop gain at all frequencies is not possible and also not desired, because eventually the frequencies are so high that we don't want them to have high gain anymore. So typically the design goal of a loop gain looks something like that. We have large values at low frequency, and then we have small values at high frequency, and of course we transit from large to small, and that means somewhere we cross the 1, and that's the 0 dB crossover frequency, or also called unity gain frequency. And there is a rule of thumb that the unity gain frequency, that the slope of the gain should be minus 20 decibels per decade. That means 10 times less gain when the frequency increases by 10 times. So it's a slope of minus 1. Because 10 times higher, 10 times lower, that's 45 degrees, and that's a slope of 1, minus 1. Now, when we have that closed loop transfer functions where we have t over 1 plus t, or the open loop transfer function over 1 plus t, we always have this over 1 plus t. So we have the 1 plus t in the denominator. And what happens if the t approaches minus 1? Then we have 1 minus 1 is 0, and the something divided by 0 is a large number, or not defined, and we could say that's instability. So we don't know what happens anymore, and what we could also say is that the negative feedback actually changes to positive feedback. So by looking at the loop gain, we can check if the closed loop system will be stable or not, and one way to check is how far away is the loop gain from that positive feedback point, or also called the critical point. And this test is also called the phase margin test. It's a special case of the general Nyquist stability criterion, and it basically says if phase margin is more than 0 degrees, then the closed loop system is stable. And how does it work? So we have the Bode plot, we have magnitude, we have phase. We look at the 0 dB gain value, we check where is the unity gain crossover frequency of the magnitude, and then we look at the phase, and then we check how far away is the phase from minus 180 degrees. Why minus 180 degrees? Because minus 180 degrees means it changes the direction. So if you have a sine wave and you shift it by 180 degrees, then it's inverted. So it's minus 1, because gain is 1, and an inversion, that's minus 1. So that's where we have the phase margin. We can also look at it in the Nyquist plot, or in the complex plane. We have the unity gain circle. That's where we have the gain of 1. So that's where the transfer function crosses the unity circle. That's the unity gain crossover frequency, and that would be in that case here on that slide. And then we can check how much degrees would we need to rotate the transfer function, that blue line, how many degrees do we need to rotate it so that it hits the critical point. And a rotation in phase is, for example, coming from a time delay. So if you have a time delay somewhere, if you have a digital compensator and the processor takes longer because of, I don't know, some bug or whatever, that means you lose phase. And that could be a loss of phase margin. Now, I said in the beginning, more than 0 degrees means stable, but how much phase margin is really desired? And that's a simulation that I have done a long time ago. I still use it. Here we see a simulation of a buck converter that has a crossover frequency of 40 kilohertz and a phase margin of 7 degrees roughly. And from that 7 degrees you can see a lot of overshoot and ringing. And this ringing frequency, so if we take the period of that wave that you see here that rings after the step, that is 1 over the unity gain frequency. So the unity gain frequency, the crossover frequency, is the natural frequency of the closed loop system. If you give it a step, it will respond with that frequency. And 7 degrees phase margin means very low damping. That's why we have so many rings. If we look at 23 degrees of phase margin, that looks already better. We have more damping and less rings. 31, even better. 45, even better. And when we approach values that are 70 degrees and beyond, then we don't see any ringing anymore. We have a highly damped system and there is no ringing frequency visible in the transient response. So the phase margin is not only a measure of robustness, it's also a measure of damping of the closed loop system at its natural frequency. Now let's talk about the gain margin, the second stability margin that is typically mentioned when you have a spec or when you want to check for stability. And gain margin is the amount of gain that would be needed to make the transfer function hit the critical point. So it's actually a measure of robustness. It doesn't tell us much about how the system behaves. If it's running like that, if you have more gain margin, it will not behave differently than if you have less gain margin. At least from my understanding, it's just a measure of robustness. So how much gain change can you tolerate in the system until you lose phase margin? Of course, if you lose phase margin, then the system will behave differently. So, and since they are somehow connected, it's difficult to have one without the other changing. It also changes when you change the gain. So how do we find the gain margin? In that case, we take the other route. So we look at the minus sign, the minus 180 degrees. We check where the phase hits minus 180 degrees, and then we check how much gain do we still have. So if we would shift that blue curve up, the gain curve, by the gain margin, then the phase would hit the minus 180 degrees, and having gain at 0 is 1 and minus 1 would be instability. In a theoretical second order system, there is no gain margin because the phase never reaches minus 180 degrees. You only have 2 poles. Each pole brings 90 degrees, but just somewhere approaching minus 180 degrees, so you don't have a gain margin actually. But due to extra time delay in a system and parasitics, also a typical theoretical second order system has actually more than 2 orders and it has a gain margin. We can also look at that in the Nyquist diagram. So that would be the phase margin, and the gain margin is how much gain do we need to add so that this blue transfer function starts to cross the minus 1 point. And then there is a third stability margin that is called, I think in the body suite we call it stability margin. In literature sometimes it's called vector stability margin. There are also different words for a very similar concept. And the concept of the vector stability margin is that you usually never have only gain changes or phase changes in a system coming from temperature variations or from aging of components. Usually these two things cannot only be looked at it separately, right? Gain margin only looks at the gain changes, phase margin only looks at phase, but what happens if both change simultaneously? They could change simultaneously and cause instability even earlier. And that's the idea of the vector stability margin. It's a measure of robustness that tells us how close the loop gain approaches the critical point, not only in terms of phase or gain, but also in the complex plane in total. So if the loop doesn't have that beautiful minus 20 decibels per decade shape, then it could also show some wiggles in the complex plane, and it could somewhere approach the critical point even more earlier than just for phase margin or gain margin values. When you look at the numbers, how much is typically used, a vector margin of 0.5 represents roughly 30 degrees of phase margin and 6 decibels of gain margin when you compare them to each other. So if you're striving for 45 degrees of phase margin and more than 6 decibels of gain margin, then you should also try to have a vector margin that is a little bit higher than 0.5. Here I show that in the Nyquist plot of Bode analyzer suite. When you activate the stability margin calculation, you can see this arrow that is showing us the closest point of the red transfer function, that's the gain, towards the critical point here at +1. So until now I talked about -1. Here I show you +1. This would be phase margin, 32 degrees, 41 decibels of gain margin, and a vector stability margin of 0.5 something. And I will later explain why I used the +1 here. For now, just accept it like it is. Why do we measure stability? Well, low phase margin can add significant ringing to the dynamics of the system and can degrade performance of devices that you're powering. Especially when you're powering sensitive circuits, then you should make sure that there is enough phase margin, that you don't have noise that is constantly degrading the performance of these components. Another reason to measure it is to verify simulation or verify systems to ensure stability in different operating points or different environmental conditions. But of course there are also limits to this method. The loop gain measurement is not applicable to highly nonlinear control. An example would be hysteretic control. There are different variations of hysteretic control that don't have a real compensator. It's just like bang bang control, it's on or off and nothing else, nothing in between. So there is no compensator, there is no frequency domain design, and there is no traditional way of running unstable from negative feedback. So there, of course, the loop gain measurement also does not really make sense. Also, when your circuit runs into low load modes for power saving, like burst or pulse skipping, then it can be that the system changes from a traditional linear control into a nonlinear control. And it is a small signal analysis, so it does not replace a large signal analysis like a transient response from 10% to 90% or from 0 to 100 or whatever. That's a completely different thing. Also, sometimes you cannot do it because you have internal feedback. If everything is on a chip or if you have highly integrated modules, you might not be able to access the feedback loop and to open it for the measurement. Also, in my opinion, it has limited significance in a primary side regulation. You have a control loop on the primary side, but really there is no traditional compensation that you can do typically. And also the question is, what happens to the output, right? Does it really make sense? So in such situations, I suggest to think about an output impedance measurement. Check out the Picotest website where the NISM, the non-invasive stability method, is explained. That gives a perspective that tells you more about how the load sees the power supply. And if there is an oscillation tendency in the power supply, then you will see peaks in the output impedance typically, and that so that's a way of indirectly check a power supply from looking at the output impedance instead of really trying to look into the loop. Now, how does that measurement of a transfer function really work? That's quite easy. We have our Bode analyzer that generates a sine wave. We somehow inject that sine wave into the system. It runs through the system, and then let's assume we want to measure the transfer function H2 here. Then we connect channel 1 at the input of H2 and channel 2 at the output of H2. And the analyzer will do the complex division of voltage at channel 2 divided by voltage at channel 1 over frequency, and that gives us the complex gain, and that's the transfer function, which is defined as output voltage over input voltage. Note that the signal path from output to H2, so this add AC signal here and the H1 is not part of the measurement result itself, right? The measurement result itself is dependent on where you connect the probes. Of course, you can have impacts of the absolute signal that you're injecting. It could be smaller or bigger. So you could have good signal to noise or bad signal to noise. You could have enough measurement signal or insufficient ripple, but it will not change the result itself. Yeah, and don't forget that actually we're talking about a linear system analysis tool. The Bode plot is a linear tool, so it's theoretically only applicable to linear systems, or at least to a linearized situation. So you have an operating point and you just do small signal changes around that operating point, then you can also say, okay, I'm in a linear region of my system. In the Bode analyzer suite, you use the gain phase measurement mode to use the Bode as a frequency response analyzer. That means the receiver 1 and receiver 2 are connected to the channel 1 and channel 2 connectors, and they compare two voltages. On the Bode 500 it looks pretty much the same. The method that is used for this loop gain measurement is called voltage injection. It was first presented by Middlebrook in the 70s. There is a paper in the end of the references, you can find it, that explains precisely how this measurement method works, and I would like to quickly explain it to you here. So when you have that control loop with the feedback and the compensator and the negative error amplifier, then we are basically breaking the loop by inserting an extra resistor in the loop. And then we impress the disturbance voltage that we call here VI for injection, and we use a galvanic isolation like an injection transformer to bring that disturbance into that loop. And then we measure channel 1 at the input, channel 2 at the output, and we get the transfer function from point B around the loop to point A. And if we ignore that resistor here, then we have the loop gain of the complete loop. Yeah, the resistor typically is a 10 ohm resistor or higher. On the PFC I used a 1000 ohm resistor, but I'll explain later why. Now there are, in the paper of Middlebrook and also in the book Fundamentals of Power Electronics from Ericsson and Maximowicz, you can find the detailed explanation on the math, why this measurement works and where the limitations are. And basically, by comparing these two voltages, the Bode basically measures the loop gain multiplied with a factor and added a factor. And these two factors can be ignored when the ratio of the impedances at that point where you put the injection resistor is large. And it means the impedance in loop direction must be significantly larger or much larger than the impedance backwards. That's the most important condition that this measurement gives you correct results. So when we select such an injection point in a control loop system, we need to find a suitable injection point that fulfills that condition, that the impedance in forward direction or in loop direction is significantly larger than the impedance looking backwards. Points that are typically well suited are the output of the voltage source, that's at the top of the feedback divider, the input of an operational amplifier that typically has a very large impedance, the output of an operational amplifier that typically has a very small impedance, best case, of course, between two operational amplifiers, and another condition that is important, make sure that no signal is bypassing the injection point, otherwise you're not measuring the complete loop, because there could be a parallel loop that does something else. Then don't forget about the Nyquist sampling theorem. A typical PWM converter only creates one set point per switching cycle, so that's a sampled system, and you only need to analyze that up to half the switching frequency. So the stability margins usually only need to be analyzed up to half the switching frequency. Here we would have the phase margin by looking at the gain crossover frequency, and we have the gain margin, and then typically at the switching frequency we see a discrete disturber that shows us where the switching frequency is happening. Now, I said before, we're looking at the +1 point in the body measurement and not at the -1 point, as explained before. And the reason is that we are injecting the signal in the closed loop system. So here on the right-hand side, that's the situation that we have. We inject between the power stage and the compensator in the feedback path typically. And then the signal travels through the complete loop, it runs through the error amplifier and it comes back. So we are basically measuring the loop gain as minus the product of all the gains in the loop, and not just the product of all gains in the loop. And this extra minus gives us an 180-degree phase shift, so we can think of positive feedback when we have 0 degrees phase. So if you wiggle here, goes around, comes back larger with no phase delay, then it's going to go even bigger here and get bigger and bigger. So positive feedback is happening at 0 degrees and not at minus 180 degrees when we measure a loop in the physical system. So selecting the injection point on low voltage systems, it's usually between the output voltage and the feedback divider. The feedback divider has kiloohms, hundreds of kiloohms. The output of the converter has big capacitors. So it's a small impedance and it's a big impedance forward. That's well suited. For high voltage systems, you can do the same, but it's not really nice because you have a high voltage. The injection resistor is, for example, riding on 400 volts. That's what we also do on the PFC measurement. And then you need to connect the body to that high voltage. You need 100 to 1 probes, for example, to bring down the voltage. That means you're also dividing the small AC signal by 100, and then the signal to noise ratio gets really bad. So it's not really nice. It works, but it's not good for the signal to noise ratio, and then you need to use a very low receiver bandwidth. The measurement takes a long time and it's noisy. If you have higher power systems, then typically you can search for a signal conditioning chain, an active one. After the feedback divider, there is often a buffer amplifier that then drives some ADC or whatever, and some filtering is happening. And in that signal conditioning chain, that is typically 0 to 5 volts or something like that, you can inject easily. If you find a point that is suitable there, that's the best case scenario for a high voltage system. On very low voltage systems, please check that there could be remote sensing that happens, and often even a differential sensing to get rid of the loss on the ground. And then you also need to use the same reference as the controller is using, and you might need to use differential probes to avoid grounding issues. And if you have digital control, then just don't inject directly at the ADC pin. The ADC pin can be very sensitive also to common mode noise. And if you connect the entire body assembly to that ADC pin, then you could have issues from noise that is coupling in. Yeah, the injection signal size is a critical value. What is important to remember there is the result must be independent on of the amplitude, otherwise we are not measuring in a linear region anymore. That means typically we choose an injection level, we measure, then we change the level and we check is the result still the same, and if not, we need to further reduce. So that's how you can bring a very corrupted result to a clean result that represents small signal behavior and not large signal behavior that is impacted by some slew rate limitations or some saturation of something. For the large signal analysis, use the scope. Then often you hear there is a lot of noise at low frequency. Also in the measurement before, in the graph we have seen there is a lot of noise at low frequency. And the reason is that we are injecting a small signal here, and the control loop is trying to keep that feedback point stable. So it will react at the output voltage with an inverse action of that what we inject, and it will try to compensate what we are injecting. That means that at the feedback point, nearly nothing is left. And measuring the phase ratio between nothing and something is tricky, especially when there is switching noise. So if you have a gain of 60 decibels in a loop, that's a factor of 1000. Every 20 decibels is a factor of 10. And if we inject 30 millivolts, for example, then the channel 2 needs to measure 30 microvolts, and it needs to measure the phase ratio or the phase delay between a 30 microvolt signal and a 30 millivolt signal. And that's tricky, right? So if you inject 300 millivolts, then suddenly channel 2 gets, I think there is an error here, gets 300 microvolts, that's 0.3 millivolts, and then it's getting easier. Yeah, so at low frequency, typically you need to use more power, and that's why we have the shaped level feature, that you can inject more signal at low frequency to also have less noise at lower frequency measurements. Some people don't like the dBm unit. I just accept that it's there. It has its advantages, in my opinion. If you don't like it, you can change the default level unit of Bode to volts, and if you make a new file, it will be showing the output level in volts. But anyhow, the real voltage that you're injecting will depend on the injection resistor that you connect. And here I have a graph that shows you between 1 ohm and 1000 ohm injection resistor values, the relation between the injection signal level in dBm and the voltage that is going to be injected on your system. Up to 25 dBm, that's the maximum that you can do when you use Bode with BM12 amplifier. So the maximum is something around 8 volts RMS. For the phase wrapping, that's something that also sometimes causes confusion at low frequency, especially when the phase is close to minus 180 degrees. Then there are these peaks in the measurement, or phase jumps, we can call them. That means that when we look at two waveforms, we cannot really distinguish if they are like shifted by plus 180 degrees or by minus 180 degrees just by looking at them. And that means if there is a little phase noise on the result, then it could jump between that situation and that situation. And that's why Bode is plotting these values where they are and then drawing a line between them. That just means that there is a little bit of phase on the result and it's close to 180 degrees. It can be a large visual effect. You can click on unwrap phase and then the software will clean that up. It will say, okay, we have a continuous phase, so the phase will go above 180 degrees also. But there is a disadvantage here, and that is what happens when the first value is at minus 180 and not at plus 180, then it could cause the entire curve to shift by 180 degrees. You can solve that by just ignore that the phase wrapping happens, or by reduce the phase noise, or by sweeping backwards if the starting value at high frequency is stable. Typically, calibration is not necessary, and if you are not sure if your probes are adjusted well and you get the clean result, then just connect both probes to the output of the Bode, and then you should get a clean 0 decibels and 0 degree curve. Also, make sure that you consider the input filter and the load. The input filter can impact stability, and the load can also act with the loop. If you have an active load that is having a control loop in itself, then it could interact with the loop. So check that you have the conditions that you also expect later on. And now we're moving closer to the PFC, and the first thing I would like to add are some words on safety. Please make sure that you follow all the rules and laws that are applicable to your workplace when it comes to electrical safety. And this sign, this arrow triangle, doesn't mean danger, it means read the user manual. And in the user manual, you will find the safety information, or the notices, warnings, and caution. Warning, death can occur, or caution, minor or moderate injury may occur. So, Bode 100 and Bode 500 are self devices. Self stands for safety, extra, low voltage, and that's also written in the user manual. Bode is a self device, and you should not apply voltage levels above 50 volt DC or 25 volts AC to the inputs of the Bode, no matter if it's 100 or 500. When working with external voltage, ensure that they cannot exceed the self levels and provide appropriate isolation to other hazardous circuits such as the AC line voltage. So what do you do if your DOT is above self-voltage levels? First, check the rules that are applicable to your test setup in general. Second, take appropriate measures, such as a physical barrier between the danger zone and the safe area. Also, connect the ground terminal in the back of the body to the laboratory ground using a solid connection. That helps with the GFCI protection. And don't forget that the USB of the body is connected to the housing, which is connected to the BNC shields, which is connected to your laptop or to your computer that is connected to ground if it's a desktop computer, to protective earth over the desktop computer. That's not a safe protective earth connection, by the way. It's just there. Just be aware that it's there. So you must use appropriate isolation between the DOT and the body. And the BVIT and the BLFT, so our injection transformers, are rated for isolation up to 600 volts and in category 2. So you could use it on a system that is connected to a power socket in a household. And use active high voltage differential probes if you want to be safe. Then you have absolute isolation between the hazardous voltage and the body. An example of such a setup that goes up to 600 volts DC, because the BVIT and the BLFT are rated to 600 volts DC, could look like that. We have the power stage with the dangerous voltage. We have the injection on the hazardous voltage level. We have the injection transformer. And note that if you connect one point of the injection transformer, the other one will also be on high voltage. So do never connect when the system is live. And then we have the differential probes that are rated to the safe voltage or to the voltage that you experience. And then after this isolation, we have the safe area where we can connect our vector network analyzer and the computer and be safe when operating it without having the danger of the system. One way to increase safety is also using galvanically isolated sources. Power supplies that are used in labs are typically isolated from mains. If you don't have that, you could also use an isolation transformer or a variable transformer that can provide galvanic isolation. Here is a picture of an example that I used for the PFC measurement. Yeah, probes. One word on probes. Don't use 10-to-1 scope probes with the body 100 or body 500. A standard scope probe that is coming with such an oscilloscope will not divide the DC signal when used with body 100 or body 500. The reason is the input of the body has AC coupling before the 1 megaohm termination. That means that if you have a standard probe that has a 9 megaohm dip resistor, for DC signals, the 1 megaohm of the input of the body is not visible because it's blocked by the AC coupling capacitor. Therefore, our probes, the probes that we sell for body 100 and 500, have the divider in the tip also to divide the DC voltage to a safe level. We have the PML and the PHV probe. Yeah, and before we talk about probes, before we talk about the PFC, don't forget that the ground clip of the probe is always directly connected to the housing of the analyzer. So when you work on hazardous voltages with passive probes, then it's mandatory or very important that you have an isolated source that is isolated from mains. Otherwise, you can only connect the ground clip to a real ground. But in such a system, there are not many points where you have a real ground. Now let's talk about the example that I mentioned in the beginning. I tried to measure a PFC voltage loop, the V-bus loop, for the 400 volts bus voltage of a PFC converter. It's a board from MPS, and you see it here. It's something like a laptop power supply example, and it has a universal input, and it generates 19.5 volts at 9.2 amps output current. We have here the PFC inductor, some filtering, and then there is a second LLC that is connected that brings down the 400 volts to 19.45 volts. So the bus voltage is 400 volts DC. It has a ripple of 100 Hertz, double the line frequency, a quite significant ripple. The voltage loop is slow, only just 15 Hertz crossover frequency. So we start the measurement at 1 Hertz. And we have no signal conditioning circuit, so the injection point is not very beneficial. So let's look at the injection point in the schematic. Here we have the input that goes into the input filter. Then we have here the boost inductor. We have the power switch, the boost diode, and then we have here the 400 volt bus voltage. Then here we have the feedback divider, and the blue signal goes to the control chip. So that's the control chip, and there is no buffering, there is nothing. The feedback divider has a very high impedance, so the only way we can measure the loop is by putting the injection point here on top of the feedback divider. So let's look at that a little bit more detailed. So we have nearly 10 mega ohms of impedance in the feedback divider, so we can easily put a 1 kilo ohm resistor here without changing the conversion, the division ratio, and then the signal from the body will be driven into the BLFD, inject across the 1 kilo ohm injection resistor, and we have two 100-to-1 differential probes that bring down that signal so that we can connect it safely to the channel 1 and channel 2 of body 100. So here the test pins, I soldered a 1 kilo ohm injection resistor in the feedback trace, and I glued on some test pins to make probe connection easier. In the end it looks something like that. We have the injection points here, and then we have the negative, which is not ground by the way because it's after the full bridge rectifier. Then we have the V bus voltage that goes to the probes, channel 2 and channel 1. So body 100 here, that's a self device. We have the PFC DOT that is hazardous. We have the LFD injection transformer, two high voltage differential probes to connect channel 1 and channel 2 of the body to the hazardous voltage, and an isolation transformer as an adjustable AC source so that we can vary the voltage level and also have isolation to mains. And in Austria we need a warning sign. In addition, I put the protective earth connection to the housing of the body 100. In the body 100 we use the gain phase measurement mode, start at 1 Hz, stop at 1 kHz or less, 201 points, don't use too many points on such a slow measurement, and set the receiver attenuators to maximum sensitivity, 0 decibels, since we are using 100-to-1 probes. And I used receiver bandwidth of 1 Hz for maximum filtering. And the signal level depends a little bit on the application. Here I used the maximum signal level. Also, I tried using the BLFD with the B-amp, and if you look at the user manual, you can see at 1 Hz you can use up to 15 dBm signal on the BLFD without having too much distortion on the measurement, and from 2-3 Hz on you can use the full 25 dBm. Here at 100 Hz I had to reduce the injection level a little bit in order to avoid overlapping between the ripple, the 100 Hz ripple on the V-bus, and the injection level, otherwise my body was showing an overload. So to avoid saturation below 3 Hz, I have reduced the injection level a little bit at low frequency, and that's the results that I got. So here I measured at 100 volts input and 2 amps output, so that's like low input and low output load, and up to 200 volts input, 9 amps output, that would be maximum input and maximum output load. And as you can see, the crossover frequency is always around 14 to 15 Hz, and phase margin is always around 60 degrees. So that's a system that employs a digital control loop, and that digital control loop can basically adapt the compensator so that the system behaves the same in every load input and output, input line and output load condition. So it's a very stable control that has the same dynamics in all the operating conditions. Here at 100 Hz we have the ripple of the bus voltage, so that gives us a disturbance, a spike here, and then 200, 300, 400, 500, another one here. That was not there always. Yeah, so let's try such a loop measurement in real life, but as I said in the beginning, I'm not going to do it on the PFC because the sweep takes long at 1 Hz bandwidth with 201 points. That takes roughly 8 minutes for one sweep to complete. I only have 6 minutes or 7 minutes left, my watch says. So let's do a different measurement. And we use demo board. I have here the converter stability demo board that employs a dual buck converter. So we have 5 volts input. We have an input filter stage where we can add or remove the damping of the input filter. And then we have a 1.8 volt and a 3.3 volt output and a load for each of these converters. I'm currently connected to the 3.3 volt converter that also features a ferrite bead in the output, and you can see that later. So the input filter has some polarity protection and LED and some damping. And then we have the load, which is just causing some resistive load. Also a small transistor to do some load stepping that I can show transient response on the oscilloscope. And the converter itself is a chip that has the switches inside. So we just have the output filter, we have the storage inductor, we have the output capacitor, a ferrite bead and a second decoupling capacitor. And then we have the feedback divider here, 200 kilo ohms and 100 kilo ohms. And here we have an injection resistor. In that case, it's a 1 ohm injection resistor because we don't need a lot of signal. And the smaller the injection resistor is, the smaller the injected signal will be. And the connection of body of the BWIT 100 goes to these 2 points, and also the input connection goes to these 2 points, and the reference is ground. Yeah, and let's try that in real life. First, I'm gonna stop my share and try to share my setup with you. So that's the setup. I have the Bode 500 here. This is the device under test, our test board. Then I have the injection transformer here to inject the signal into the feedback network. Then the channel 1 and channel 2 connection. Since the voltage is so low, I just use a direct one-to-one connection with some test clips. Don't even need a probe, a special one. Then we have an oscilloscope to monitor the output voltage, to make some load stepping. I take off the load stepping for now. Just remove that connection. And that's basically it. Power supply comes here from the USB-C connection, and then we have 5 volts and 3.3 volts at the output. Now back to our Bode. First thing when we start Bode is, that was the PFC measurement. I don't need that at the moment, so I'm gonna select File, New Measurement. Then I have to choose my device. Here is my Bode 500. And then I use the gain phase measurement mode. I select that measurement. Don't need the previous file anymore. It employs the connection to the Bode analyzer suite, to the Bode 500. And the first thing that we do is select the frequency range. In that situation, it's a quite fast control loop, so let's go from 100 kilohertz to 1 megahertz. The switching frequency is at 700 kilohertz, so I don't go higher. And well, I think that's basically it. So let's press the single sweep button, and something doesn't work, of course. That's the effect of a demo. Live demo. 100 kilohertz, that was the mistake. 100 hertz I wanted to do. Let's press start again, and then we get a blue and a red curve. I right click optimize, and I prefer to switch to 1 axis per chart here. Then we have a magnitude curve here in the upper graph, and we have a phase curve in the lower graph. And as said before, we have a lot of noise at low frequency, we have a lot of phase noise at low frequency, and if we click on unwrap phase, that will change these phase jumps, but it will add a new problem. Let me run the measurement again. You see now the first value was a lower value, that's why it's jumping around now. So I don't care about that phase jumps, I know these are not relevant. Also when I look at stability, only at phase margin and gain margin, I don't need this low frequency area actually. What can we do to clear it up? We can use a lower receiver bandwidth. Let's use 100 hertz, then we have less noise. We could even use even less, but then the sweep takes longer. Now it takes 5 seconds. I don't want it to be slower now. So what we can also do is we can use more signal. So I can increase the source level, and then the result will also get clearer. First thing I'm going to do now is store a memory and check, are we already too high? I'm going to increase by 4 decibels more. And now I can start to see, let's go even higher, that at the crossover frequency here we get a little deviation if we increase the signal too much. So that's too much. Let's go back to the 6 dBm, and that's for now the result or the signal that is acceptable for me. At low frequency we could use more, so I select variable signal, shape level, and we see here below 2 to 3 kilohertz, that's where the noise starts. There we could use more signal, so let's give a double click here and more signal below that, and then the curve should be even cleaner. Good, for now I think that's enough. I'm going to update the memory here, and as a next step I would look at the gain margin and phase margin. So I go to cursor, select stability margin calculation and track margins, and now it will tell me I have 16 degrees or 17 degrees of phase margin and 15 decibels of gain margin and a vector stability margin of 0.3. So the stability is not great, but I do have a switch here where I can switch between a good compensator design and a bad compensator design. So now I switched to the good compensator design, and now we have 50 degrees of phase margin and a vector stability margin of 0.7. Also we have an input filter here. If I disable the input filter damping, then we can see that we get another impact of the loop gain at 10 kilohertz. So we get the second crossover, and things are looking ugly now. I'm going to switch to the scope soon that you can see the impact of that. First, I'm going to damp it again and bring on the scope screen for you. Stop the sweep here, and here is the oscilloscope. So now I connect the load stepping to the output. So we're doing a small signal load step, repetitive, and the oscilloscope is triggered to the load step, so we can average out the switching noise. And you see that's 50 degrees of phase margin, and now I switch back to 16 degrees, and now we can see a clear ringing that is triggered at each step, and the ringing frequency equals the crossover frequency that was at roughly 21 kilohertz. Yeah, if we zoom in, you can also see another higher frequency triggered at each step, and that's the second stage output filter, the ferrite bead. If I disable the ferrite bead by switching on here, then this first ringing is gone, but the second ringing from the control loop, the lower frequency, is still there. So this second stage LC filter ringing is not related to the control loop itself. It cannot be seen in the control loop gain, but it could be seen in an output impedance measurement. Yeah, that was just a very quick stability margin measurement. Doesn't take a lot of time if everything is prepared well, of course. If you're interested in more information, please check out the references that are coming with that presentation. And with that, I say thank you for your attention and sorry for taking too much time.